Picture this. You're an astronomer, and you've just pointed humanity's most powerful telescope at a patch of sky that's supposed to be, well, boring, empty space. The kind of region that textbooks call a cosmic void, basically the universe's version of a vacant lot between neighborhoods. You're not expecting fireworks. You're definitely not expecting to find anything that rewrites the rules of physics, but then your screen lights up with something impossible. 500 stars, burning bright. In a place where stars have absolutely no business existing, not just unlikely stars, not just rare stars, physically impossible stars according to every equation we've spent decades perfecting. These objects are violating the fundamental laws of stellar physics, the rules that govern how matter organizes itself into stars across the entire universe. Imagine walking into an empty kitchen with nothing but air and bare counters, and finding a perfectly baked loaf of bread just sitting there, hot, fresh, impossible. That's what's happening 4.6 billion light-years away from where you're sitting right now, and it's about to change everything we thought we knew about how stars are born. Chapter 1. Stellar Birth. To understand what makes these 500 stars impossible, we first need to establish what normal star formation looks like. This isn't abstract theory. We've observed stellar nurseries throughout our galaxy with remarkable clarity, watching the birth of stars in real time across millennia. Star formation begins in giant molecular clouds, vast regions of space where hydrogen gas accumulates at densities far higher than the near-perfect vacuum of interstellar space. The Orion Nebula, located approximately 1,350 light-years from Earth, provides the perfect laboratory. This stellar nursery spans roughly 24 light-years across and contains enough raw material to create thousands of stars. When you look at Orion through even a modest telescope, you're witnessing creation itself, the same fundamental process that formed our Sun 4.6 billion years ago. The physics governing this process follows a precise sequence. Within these molecular clouds, random density fluctuations create regions where gravity begins to dominate. As more gas falls inward, the region's gravitational pull strengthens, accelerating the collapse. This would continue indefinitely except for one crucial factor: pressure. As the cloud contracts, particles collide more frequently, generating heat and outward pressure that resists gravitational collapse. This battle between gravity pulling inward and pressure pushing outward determines whether a star will form or the cloud will simply disperse. Here's where metallicity enters the story and why it's so critical to understanding our impossible stars. Metallicity refers to the abundance of elements heavier than hydrogen and helium. In astronomy, everything heavier than helium is classified as a metal, including carbon, oxygen, nitrogen, and iron. This seems like strange terminology until you understand its significance. These heavier elements act as cosmic refrigerators. When hydrogen atoms collide with metal atoms, they efficiently radiate away energy as infrared light, cooling the gas cloud. Cooler gas means lower pressure, which allows gravity to continue pulling the cloud inward until densities and temperatures in the core reach the threshold. For hydrogen fusion, roughly 10 million Kelvin, the numbers tell a compelling story. In regions of our galaxy with solar metallicity, meaning metal abundance similar to our Sun's, star formation proceeds efficiently. Molecular clouds cool rapidly, contract to high densities, and ignite fusion relatively easily. But when astronomers observe regions with extremely low metallicity, like certain dwarf galaxies in the early universe, star formation rates plummet. The gas simply can't cool effectively without those metal atoms to radiate away excess energy. This brings us to the cosmic chicken and egg problem. The very first stars in the universe, what astronomers call population 3 stars, had zero metallicity. They formed from the primordial hydrogen and helium created in the Big Bang, with absolutely no heavier elements to assist cooling. Theoretical models suggest these objects had to be absolutely massive, perhaps 100 to 1,000 times the mass of our Sun, because only under extreme gravitational pressure could pristine hydrogen clouds contract enough to ignite fusion. These behemoths would have lived fast and died young, exploding as supernovae within a few million years, seeding space with the first metals. Every subsequent generation of stars benefited from this enrichment. Population 2 stars, formed from gas clouds containing trace amounts of metals from population 3 supernovae, could achieve star formation more easily. Population I stars like our Sun, born from gas enriched by billions of years of stellar death and rebirth, live in a universe where metal abundance makes star formation almost routine given sufficient gas density. Dr. Robert Kirshner, former director of the Harvard-Smithsonian Center for Astrophysics, describes this progression elegantly. The universe learned how to make stars more efficiently over time. Each stellar generation was a test run for the next. By the time our Sun formed, the recipe had been refined over 9 billion years. Now consider what we observe in regions of active star formation today. The Eagle Nebula's pillars of creation, photographed famously by Hubble and recently re-imaged by JWST with stunning clarity, shows dense columns of gas and dust where stars are actively forming. Spectroscopic analysis reveals metallicity levels approximately half that of our Sun, still orders of magnitude higher than primordial gas. Young stars embedded within these pillars exhibit the exact formation patterns our models predict. Fast-rotating protoplanetary disks surround them. Jets of material shoot outward along magnetic field lines. Everything proceeds according to the textbook sequence. The Atacama Large Millimeter Array in Chile has given us even more detailed views. By observing at millimeter wavelengths, ALMA penetrates the dust that obscures stellar nurseries in visible light, revealing the intricate structure of collapsing clouds. In 2019, ALMA captured images of a protostar designated IRAS 1629324222, located about 400 light-years away in the constellation Ophiuchus. The observations showed a young star still gathering material from its surrounding disk, with clear evidence of organic molecules, including sugars and amino acid precursors, forming in the warm regions near the star. This is star formation as we understand it, methodical, predictable, following physical laws we can measure and model. But here's the critical threshold that defines what's possible. Based on thousands of observations and decades of theoretical work, astrophysicists have established minimum metallicity requirements for efficient star formation. The consensus holds that metallicity must reach at least 0.01 times solar metallicity, 1% of our Sun's metal content, for normal star formation to proceed. Below this threshold, gas clouds struggle to cool efficiently, preventing the high densities required for fusion ignition. This isn't controversial theory, it's observational fact, supported by surveys of thousands of galaxies across cosmic time. When astronomers study the most metal-poor environments we can observe, ancient globular clusters, certain dwarf galaxies, remnant gas from the early universe, they consistently find this pattern. Star formation becomes progressively more difficult as metallicity drops. In systems with metallicity below 0.01 times solar, star formation essentially ceases entirely. The universe simply doesn't provide the physical conditions necessary to cool gas clouds to the required densities. This framework has held firm for 50 years of astronomical research. It's been tested against observations from Hubble, Spitzer, Chandra, and numerous ground-based telescopes. Computer simulations incorporating detailed physics of gas dynamics, radiative cooling, magnetic fields, and turbulence all confirm the same conclusion. There exists a hard floor on star formation tied directly to metallicity, until 500 stars decided to ignore these rules entirely. These objects shine from regions where every model says darkness should prevail. Their spectroscopic signatures show metallicity readings of 0.0008 times solar, 40 times below the theoretical minimum for star formation, deep into territory where stellar birth should be physically impossible. Yet there they burn, hydrogen fusing into helium, generating light that traveled 4.6 billion years across expanding space to reach JWST's infrared detectors. The question now transforms from how do stars form to something more unsettling. What fundamental aspect of stellar physics have we misunderstood so completely that 500 stars can exist where we declared existence impossible? Chapter 2. Webb's Vision. The James Webb Space Telescope didn't stumble upon these impossible stars by accident. Discovery required arguably the most sophisticated astronomical instrument humanity has ever launched into space, operating at the absolute edge of its capabilities. To appreciate what Webb detected and why no previous telescope could have found these objects, we need to understand exactly what makes this observatory revolutionary. Webb launched on December 25, 2021 from French Guiana aboard an Ariane 5 rocket, culminating a development program that spanned 3 decades and cost approximately $10 billion. But this wasn't simply an expensive telescope. It represented a fundamental shift in how we observe the universe. While Hubble Space Telescope, launched in 1990, primarily observes invisible and ultraviolet light, the same wavelengths our eyes detect, Webb specializes in infrared radiation, light with longer wavelengths than human vision can perceive. This design choice stems from a profound astronomical reality. The universe is expanding, and as it expands, it stretches the light traveling through space. Light emitted by distant galaxies gets shifted toward longer, redder wavelengths, a phenomenon called cosmological redshift. Objects at extreme distances emit most of their light in the infrared by the time it reaches us, regardless of what wavelength they originally emitted. To see the early universe, you must observe in infrared. Hubble could glimpse this realm, but Webb was purpose-built to dominate it. The numbers defining Webb's capabilities are staggering. Its primary mirror spans 6.5 meters in diameter compared to Hubble's 2.4 meters, providing roughly 7 times more light-collecting area. This mirror consists of 18 hexagonal beryllium segments coated in microscopic layers of gold, each aligned to nanometer precision by motorized actuators. Gold reflects infrared light with exceptional efficiency, over 98% reflectivity at Webb's target wavelengths. The entire mirror assembly weighs just 705 pounds despite its enormous size, achieved through precision engineering that carved intricate support structures into the beryllium substrate. But collecting light is only half the challenge. Infrared astronomy faces a fundamental problem: heat. Everything warmer than absolute zero emits infrared radiation, including the telescope itself. If Webb operated at room temperature, its own infrared glow would completely overwhelm the faint signals from distant cosmic sources, like trying to see stars while standing next to a bonfire. The solution required unprecedented thermal engineering. Webb orbits at Lagrange Point 2, approximately 1 million miles from Earth, always positioned so Earth blocks direct sunlight. A tennis court-sized sunshield, 5 layers of Kapton film, each thinner than a human hair, protects the telescope, creating a temperature differential of more than 600 degrees Fahrenheit between the sun-facing and space-facing sides. On the cold side, where Webb's instruments operate, temperatures hover around 40 Kelvin, minus 388 degrees Fahrenheit, cold enough to liquefy oxygen and nitrogen. At these temperatures, Webb's own infrared emission drops to nearly undetectable levels. The near-infrared camera, or NIR-CAM, serves as Webb's primary imager and the instrument that detected our impossible stars. NIR-CAM observes wavelengths from 0.6 to 5 microns, a range spanning from deep red visible light through mid-infrared. Dr. Marcia Ricci of the University of Arizona led NIRCam's development, creating a detector system capable of capturing images with unprecedented sensitivity. The camera employs 10 mercury-cadmium telluride sensors, each containing roughly 4 million pixels optimized for infrared detection. When NIRCam captured the SMACS DO17-3 field in June 2022, one of Webb's first deep-field images released. Publicly, it wasn't aiming for empty space. The primary target was the galaxy cluster itself, a gravitationally bound collection of hundreds of galaxies whose combined mass bends space-time, creating a gravitational lens that magnifies more distant objects behind it. This gravitational lensing effect, predicted by Einstein's general relativity and observed countless times since, allows astronomers to study incredibly distant galaxies that would otherwise be too faint to detect. The observation required 12.5 hours of total integration time across multiple filters, each tuned to specific infrared wavelengths. This might seem brief compared to Hubble's deepest exposures, which accumulated over 100 hours of observation time for the ultra-deep field. But Webb's superior sensitivity meant that 12.5 hours with NIRCam revealed fainter objects than Hubble could detect in days of exposure. The resulting image captured galaxies existing just 400 million years after the Big Bang, closer to cosmic origins than anything Hubble had ever clearly resolved. But Dr. Emma Whitford wasn't studying those ancient galaxies. She was analyzing spectroscopic data from the Near-Infrared Spectrograph, or NIR-SPEC, Webb's other primary instrument. While NIRCam captures images, NIR-SPEC splits light into its component wavelengths, creating detailed spectra that reveal an object's chemical composition, temperature, motion, and physical conditions. NIR-SPEC can observe 100 objects simultaneously using a micro-shutter array, a grid of 250,000 tiny shutters, each measuring 0.2 by 0.4 millimeters, that can open and close independently to let light from specific targets pass through while blocking everything else. Whitford had programmed NIR-SPEC to capture spectra from a region beyond the main galaxy cluster, an area classified as a void in cosmic large-scale structure surveys. Voids are the immense empty spaces between the filaments and clusters where galaxies congregate. Imagine the universe as a cosmic sponge, with galaxies forming the solid structure and voids as the empty pockets. These regions typically contain less than 1/10 the galaxy density of average space, and their gas content registers even lower, dispersed into a tenuous fog by billions of years of cosmic expansion. Nobody expected to find active star formation in such regions, but NIR-SPEC's mid-infrared instrument, or MIRI, detected clear emission at 4.05 microns, the precise wavelength produced by hot hydrogen gas as electrons transition between energy levels in atoms heated by nearby star formation. This signature, called the bracket alpha line, is unmistakable. It only appears around young, hot stars energetic enough to ionize surrounding hydrogen, causing it to glow. Cross-referencing this spectroscopic detection with NIRCam's imaging data revealed point sources, objects too small to show any visible structure, appearing as single bright pixels even in Webb's sharp images. These point sources exhibited spectral energy distributions, how their brightness varies across wavelengths, consistent with stellar objects in the mass range of 10 to 50 solar masses. Not quite the hypothetical population 3 supermassive stars, but still substantial young stars in their main sequence phase, actively fusing hydrogen. The spectroscopic analysis provided the smoking gun. By measuring absorption lines, dark gaps in the spectrum where specific elements absorb light, Whitford's team could determine chemical composition. They identified hydrogen, obviously present, and helium in ratios matching primordial abundances from Big Bang nucleosynthesis. But the metal lines were virtually absent. Iron, oxygen, carbon, silicon, all the elements that should be present even in trace amounts if these stars formed from recycled material. Registered at levels barely above NER-SPEC's detection limits, the team calculated metallicity at 0.008 times solar. To put this in perspective, the most metal-poor stars ever found in our Milky Way galaxy, ancient population 2 stars formed in the galaxy's earliest days, have metallicities around 0.1 to 0.1 times solar. These Milky Way stars are considered precious relics, fossil records of near primordial conditions. Yet they're ordinary population 2 objects, formed in dense galactic environments where star formation is routine. Our impossible stars match or exceed this metal poverty while forming in regions where no star formation should occur at all. Webb's infrared capabilities proved crucial for another reason. These objects, located 4.6 billion light-years away, emitted their light when the universe was approximately 60% its current age. Cosmological expansion has redshifted their light significantly, wavelengths stretched by a factor of roughly 0.5, designated as redshift Z, it chunt 0.5 in astronomical notation. Light emitted in the ultraviolet and visible range has been shifted into the near and mid-infrared, precisely where Webb excels. Hubble, with its visible light focus, might have detected the brightest of these objects but would have missed the spectroscopic details necessary to identify their anomalous nature. The discovery underscores a truth about modern astronomy. Sometimes the most revolutionary findings hide in data collected for completely different purposes. Whitford wasn't searching for impossible stars. She was conducting a routine survey of void environments to measure background radiation levels. But Webb's unprecedented sensitivity revealed a phenomenon that nobody predicted, that no model anticipated, that fundamentally challenges stellar formation theory. Now the question shifts from what Webb detected to what it means. 500 stars burning where physics says they shouldn't. What allowed them to form? What physics are we missing? And what does their existence tell us about the universe's hidden mechanisms? Chapter 3: Impossible Condition. Let's be absolutely precise about what makes these stars impossible. This isn't hyperbole or exaggeration for dramatic effect. The physical conditions in cosmic voids categorically prohibit star formation according to every model we've developed, tested, and refined over 5 decades of astrophysical research. Understanding exactly what rules these objects violate will illuminate just how profound this mystery truly is. Begin with gas density, the most fundamental requirement for star formation. In stellar nurseries like the Orion Nebula, molecular clouds achieve densities of roughly 10,000 to 100,000 hydrogen molecules per cubic centimeter. This might sound sparse. Earth's atmosphere at sea level contains approximately 2.5 x 10⁻19 molecules per cubic centimeter. But in astronomical terms, this represents dense matter. The average density of interstellar space in our galaxy measures around 1 atom per cubic centimeter. Stellar nurseries are local density peaks, gravitationally bound concentrations of matter. Now consider voids. Cosmological surveys mapping the three-dimensional distribution of galaxies have revealed the universe's large-scale structure, a cosmic web of filaments and sheets where galaxies cluster, separated by enormous empty regions. The Boötes void, discovered in 1981, spans approximately 330 million light-years in diameter and contains only 60 galaxies in a volume where we'd expect 2,000 based on average cosmic density. Gas density in void interiors drops to approximately 0.1 atoms per cubic centimeter, 10 times less dense than already sparse galactic interstellar space. The void containing our impossible stars shows similar characteristics. Analysis of galaxy counts and gravitational lensing maps indicates matter density in this region reaches only 15% of cosmic average. Gas density measurements derived from absorption line studies where background quasar light passes through void space confirm densities around 0.08 atoms per cubic centimeter. This is 1/1,000,000th the density of Orion Nebula molecular clouds. Trying to form stars from this material is like trying to build a sandcastle from individual grains scattered across a football field. But low density alone doesn't make star formation impossible, just improbable. The real barrier involves thermodynamics and the cooling problem. Gas clouds contract under their own gravity only when they can efficiently radiate away the gravitational potential energy released during collapse. This energy emerges as heat. If the cloud can't cool by radiating this heat into space, thermal pressure builds up, halting contraction long before densities reach fusion ignition thresholds. Metallicity determines cooling efficiency. When a hydrogen atom collides with a carbon or oxygen atom, quantum mechanical interactions allow the metal atom to absorb kinetic energy and re-emit it as infrared photons that escape into space. This process, called collisional excitation, followed by radiative de-excitation, effectively extracts thermal energy from the gas cloud, reducing pressure and allowing continued gravitational collapse. The more metal atoms present, the more efficient this cooling mechanism operates. Dr. Volker Brom at the University of Texas at Austin has spent 2 decades modeling primordial star formation in metal-free environments. His simulations reveal the brutal efficiency with which metallicity controls star formation. In gas clouds with solar metallicity, cooling timescales measure in thousands of years. Reduce metallicity to 0.01 times solar, 1% of the sun's metal content, and cooling timescales extend to tens of thousands of years. Below 0.001 times solar, cooling becomes so inefficient that only the most massive gas clouds, containing hundreds of thousands of solar masses, can generate sufficient gravitational pressure to overcome thermal resistance at metallicity levels of 0.008 times solar, what Webb measured in our impossible stars. Brom's models predict star formation requires cloud masses exceeding 10 million solar masses with densities maintained above 1,000 atoms per cubic centimeter for at least 100,000 years. These conditions don't exist in cosmic voids. Not even close. Void regions lack sufficient matter within any reasonable volume to accumulate such mass. Gravitational perturbations from the cosmic web's filamentary structure constantly disturb void interiors, preventing stable, dense concentrations. And the expansion of the universe itself, pulling space apart in underdense regions, works against gravitational assembly. There's another layer to this impossibility. Even if, through some unknown mechanism, gas clouds somehow achieved sufficient density in a void environment, the radiation field would inhibit star formation. Ultraviolet light from distant galaxies pervades all of space, including voids. This background radiation accumulated from billions of years of star formation throughout the cosmos ionizes hydrogen gas, stripping electrons from atoms. Ionized gas is hot gas with temperatures around 10,000 Kelvin. Hot gas means high pressure, which resists gravitational collapse. In dense environments like galactic disks, gas clouds contain enough matter that their interiors self-shield from external radiation. Outer layers of the cloud absorb incoming ultraviolet photons, protecting the dense core where stars form. But in voids, with their extremely low gas densities, self-shielding becomes impossible. Ultraviolet photons penetrate throughout the entire cloud, maintaining ionization and preventing the cool, neutral hydrogen conditions necessary for contraction. Dr. Priyamvada Natarajan from Yale University, a specialist in high redshift galaxy formation, emphasizes this point. The background radiation field acts like a thermostat set to 10,000 Kelvin across the entire volume of intergalactic space. You need extraordinary density to overcome this ambient temperature and allow gas to collapse. Voids simply don't have that density. Consider also the chemical signatures Webb detected. The spectroscopic analysis revealed not just ultra-low metallicity but specific ratios of what little metal content exists. The oxygen-to-carbon ratio measured approximately 10.1, and nitrogen abundance was essentially undetectable. This pattern matches primordial abundances, what we expect from gas that has experienced almost no stellar processing. It's the chemical fingerprint of material formed in Big Bang nucleosynthesis, barely touched by subsequent stellar generations. This creates a temporal paradox. These stars exist at redshift z √0.5, corresponding to when the universe was approximately 8.8 billion years old, more than halfway to its current age. By this epoch, multiple generations of stars had already lived and died throughout the cosmos. Supernovae had been enriching intergalactic space with metals for billions of years. Even voids, while underdense, should have been contaminated with trace metals from nearby galactic outflows and cosmic winds driven by supermassive black holes. Finding gas with near-primordial composition at this epoch is like discovering pristine mineral water in a bottle that's been sitting in a polluted river for 10 years. The spatial distribution adds yet another layer of impossibility. Webb didn't detect a single anomalous star or even a small cluster. It found 500 objects spread across approximately 50,000 cubic light-years of void space. This isn't an isolated fluke or singular bizarre event. It represents an apparently common phenomenon within this particular void, suggesting whatever mechanism creates these stars operates systematically rather than as a rare accident. Statistical analysis makes the situation even more perplexing. Dr. Whitford's team calculated that if these stars formed through any conventional process, we should observe roughly one such object per billion cubic light-years of void space, a rate so low that detecting 500 in a small region would require extraordinary luck, equivalent to winning the cosmic lottery. Yet there they are, burning steadily, challenging every model. Perhaps most disturbing is that these stars appear young. Their spectral characteristics, particularly their color temperatures and luminosities, indicate ages of approximately 10 to 100 million years. These aren't ancient relics from the early universe that somehow survived in isolation. They formed relatively recently in cosmic terms within the past percent of cosmic history. Whatever mechanism created them is active now, operating under present-day physical conditions. Some astronomers initially suggested these might be ejected stars, objects formed in dense galactic environments that were gravitationally flung into void space through dynamical interactions. But the sheer number of objects makes this implausible. Ejecting 500 stars into a small void region would require an impossibly violent galactic collision event nearby. Moreover, ejected stars would retain the metallicity of their birth environment. These objects show primordial composition, incompatible with galactic origins. Every avenue of conventional explanation hits a wall. Standard star formation physics cannot account for these observations under any reasonable scenario. We're forced to confront an unsettling reality. Either our understanding of stellar birth contains fundamental blind spots, or the universe operates under physical principles we haven't yet identified. The 500 impossible stars aren't asking us to modify our models. They're demanding we reconsider foundational assumptions. What mechanisms could possibly explain their existence? Let's explore the most compelling theoretical proposals. Chapter 4. Dark interactions. When conventional physics fails to explain an observation, astronomers often turn to the universe's most mysterious component, dark matter. This invisible substance comprises approximately 85% of all matter in the cosmos, yet we've never directly detected it. We know dark matter exists only through its gravitational effects, the way galaxies rotate, how galaxy clusters bend light, the pattern of cosmic microwave background fluctuations. It's the cosmic elephant in the room, massively influential yet frustratingly hidden. Could dark matter interactions somehow enable star formation where it should be impossible? The dark matter hypothesis for our impossible stars comes from Dr. James Bullock at the University of California, Irvine, whose work focuses on dark matter's role in structure formation. His proposal suggests that cosmic voids aren't actually empty of dark matter, just depleted compared to dense regions. Computer simulations of cosmic evolution show that even voids contain dark matter halos, gravitationally bound clumps of dark matter ranging from thousands to millions of solar masses. These halos are invisible, detectable only through their gravitational influence on surrounding matter. Bullock's mechanism works like this. A dark matter halo drifts through void space, its gravity creating a subtle gravitational well. Over hundreds of millions of years, this halo slowly accumulates the sparse gas pervading the void, gradually increasing local gas density. Eventually, the halo might collect enough material that regions within it reach the density threshold for gravitational collapse. The dark matter essentially acts as an invisible gravitational seed, concentrating diffuse gas until star formation becomes possible. This theory offers elegant solutions to several mysteries. First, it explains why star formation occurs in regions where visible matter density seems far too low. The dark matter provides the additional gravitational binding energy needed to compress gas clouds to fusion-triggering densities. Second, it accounts for the spatial distribution of the 500 stars. If they formed within a single large dark matter halo or several smaller halos clustered in one region, their proximity makes statistical sense rather than requiring impossibly lucky coincidence. The metallicity question finds potential resolution here as well. If dark matter halos in voids have been collecting gas over cosmic timescales, they would preferentially accumulate the lowest density, most dispersed material, precisely the kind of primordial gas that has avoided contamination by metals from stellar processing. The pristine composition we observe might reflect the selective filtering effect of dark matter, gravitational capture in underdense environments. Laboratory experiments on Earth are actively hunting for dark matter particles. The LEX Zeppelin detector, operating 4,850 feet underground in South Dakota's Sanford Underground Research Facility, uses 10 tons of liquid xenon to detect the extraordinarily rare interactions between dark matter particles and ordinary matter. As of 2024, Lux Zeppelin has set the most stringent constraints yet on certain dark matter candidates called WIMPs, weakly interacting massive particles, but has not achieved a definitive detection. This experimental limitation creates a problem for our stellar explanation. If dark matter only interacts gravitationally with ordinary matter, as all current evidence suggests, it can't directly assist gas cloud cooling, the critical bottleneck preventing star formation in low metallicity environments. Dark matter can accumulate gas through gravity, but it can't extract thermal energy to reduce pressure resistance. You still need the metallicity-dependent cooling mechanisms that our observations indicate are absent. Dr. Tracy Slatier at MIT has proposed an intriguing modification. What if dark matter possesses extremely weak electromagnetic properties, not enough to show up in laboratory detectors or conflict with existing observations, but sufficient to occasionally interact with hydrogen atoms in very specific conditions? Such interactions could provide an alternative cooling mechanism, allowing gas to radiate thermal energy through a previously unknown channel. This semi-interactive dark matter model remains highly speculative. It requires new physics beyond the standard model of particle physics, introducing dark matter particles with properties specifically tuned to solve our impossible star problem. Physicists generally distrust such fine-tuned explanations. They seem suspiciously convenient, like inventing a new law of nature to explain a single observation. But the model makes testable predictions. If semi-interactive dark matter exists, we should find similar impossible star formation events throughout other cosmic voids. always associated with dark matter overdensities measurable through gravitational lensing. JWST could potentially test this by conducting deep spectroscopic surveys of multiple void regions across different areas of the sky and comparing star formation rates with gravitational lensing measurements that map dark matter distribution. Astronomers could determine whether impossible stars correlate with dark matter concentrations. If the correlation exists strongly, the dark matter hypothesis gains credibility. If stars appear in voids regardless of dark matter density, we'd need alternative explanations. There's another dark matter angle worth considering, proposed by Dr. Dan Hooper at Fermilab. His research focuses on dark matter annihilation, the possibility that when two dark matter particles meet, they mutually destroy each other, converting their mass into energy according to Einstein's E at mc2. This process would release enormous amounts of energy, potentially heating surrounding gas. But here's the clever twist. In certain dark matter models, annihilation doesn't produce high-energy gamma rays or cosmic rays that would ionize and heat gas clouds. Instead, it might generate specific wavelengths of radiation that could actually assist molecular formation or create conditions favorable for gas collapse. Hooper's calculations suggest that in regions where dark matter density reaches certain thresholds, potentially achievable even in voids, if dark matter halos concentrate sufficiently, annihilation rates could create thermal conditions that paradoxically help gas cooling. The energy released might drive chemical reactions that produce molecular hydrogen, H2, which is an extremely efficient coolant in primordial gas. Molecular hydrogen can radiate thermal energy through rotational and vibrational transitions, even in the absence of metals, providing an alternative cooling pathway. This mechanism was thought to operate only in the very early universe, before the first stars formed. Computer simulations of population 3 star formation rely heavily on molecular hydrogen cooling to explain how metal-free gas clouds could collapse. But those models assume extremely high densities available in the early universe's more compact state. Hooper's proposal suggests dark matter annihilation might artificially recreate those early universe conditions in localized regions, even in the present-day expanded cosmos. The evidence for or against this mechanism remains frustratingly ambiguous. NASA's Fermi Gamma Ray Space Telescope has been scanning the sky for potential dark matter annihilation signals since 2008. Some tantalizing hints have emerged: an excess of gamma rays from the galactic center, unusual positron ratios detected by the Alpha Magnetic Spectrometer on the International Space Station, but nothing conclusive. The annihilation rates required to explain our impossible stars would be subtle enough to evade detection by current instruments, yet strong enough to influence gas dynamics over millions of years. Dr. Lisa Randall at Harvard University offers a different dark matter perspective through her dark disk hypothesis. She proposes that dark matter might not be uniformly distributed in galaxies, but could form thin disk structures, similar to how ordinary matter settles into galactic disks. If cosmic voids contain relic dark matter structures from the universe's formation, perhaps dark matter filament, or sheets that failed to collapse into halos, these structures might create gravitational channels where gas, flowing through void space, experiences enhanced concentration. Imagine rivers of dark matter crisscrossing void interiors, invisible but gravitationally influential. Normal gas drifting through the void encounters these dark matter streams and gets gravitationally focused, like water flowing into a drainage ditch. Over cosmic timescales, these dark matter conduits could accumulate enough gas along their lengths to trigger localized star formation, creating linear or sheet-like distributions of stars, a pattern that might match what Webb observed if we had sufficient spatial resolution. Testing these dark matter hypotheses requires observations we can't yet perform with existing technology. We need gravitational lensing measurements at scales far smaller than current surveys can achieve to map dark matter distribution in void interiors. We need particle physics experiments with sensitivities orders of magnitude beyond LUX-Zeppelin's capabilities to detect subtle dark matter interactions. We need theoretical breakthroughs in understanding dark matter's fundamental nature, work that has consumed physicists for decades without producing definitive answers. Here's what makes the dark matter explanation simultaneously appealing and frustrating. It's flexible enough to accommodate almost any observation. Dark matter remains so poorly understood that theorists can propose new properties as needed to explain anomalies. This flexibility makes dark matter a powerful explanatory tool, but also raises skepticism. Are we genuinely identifying dark matter's role in these impossible stars? Or are we using dark matter did it as a placeholder explanation for phenomena we simply don't understand? The question cuts to fundamental debates in physics. Some researchers argue we should exhaust all possible explanations within known physics before invoking dark matter properties beyond its established gravitational effects. Others contend that dark matter represents 85% of cosmic matter. Expecting it to influence astrophysical processes only gravitationally might be naive. Perhaps dark matter is intimately involved in processes we've attributed entirely to ordinary matter, and our impossible stars are the first evidence of this deeper involvement. What remains certain is this: if dark matter explains these stars, it would represent the first non-gravitational signature of dark matter's influence on astrophysical processes. This would be Nobel Prize-worthy physics, transforming dark matter from an invisible gravitational scaffold into an active participant in cosmic evolution. The implications would cascade through cosmology, particle physics, and our understanding of structure formation from the Big Bang to the present. But dark matter is only one possible explanation. What if the answer doesn't lie in mysterious invisible particles, but in a force we know intimately, gravity itself? What if our impossible stars are telling us that Einstein's general relativity, tested and verified for over a century, breaks down in certain extreme conditions? Chapter 5: Gravity's Secret. General relativity has survived every observational test thrown at it for more than 100 years. From the perihelion precession of Mercury to the direct detection of gravitational waves by LIGO, Einstein's geometric description of gravity has proven astonishingly accurate. Yet physicists have known for decades that general relativity cannot be the complete story. It's incompatible with quantum mechanics. It can't explain cosmic acceleration without invoking dark energy, and it predicts singularities where its own equations break down. Perhaps our impossible stars are revealing cracks in gravitational theory that only appear under specific, rare conditions. Modified Newtonian dynamics, or MOND, emerged in 1983 from Israeli physicist Mordechai Milgram's attempt to explain galaxy rotation curves without invoking dark matter. Galaxies spin so fast that their outer regions should fly apart based on the visible matter we observe. Unless substantial invisible mass provides additional gravity, or unless gravity itself behaves differently at the extremely weak accelerations characteristic of galactic outskirts. MOND proposes that when gravitational acceleration falls below a critical threshold, approximately 10 to 10 meters per second squared, gravity strengthens relative to Newtonian predictions. For decades, MOND remained a fringe theory championed by a small group of physicists but dismissed by the mainstream. Yet, it has proven remarkably successful at predicting galaxy rotation curves without free parameters, and it correctly anticipated the relationship between galaxy luminosity and rotation velocity discovered in observational surveys. Despite this success, MOND struggles with larger scales. Galaxy clusters and cosmological observations strongly favor dark matter explanations. Dr. Stacy McGaw at Case Western Reserve University, one of MOND's most prominent advocates, has recently proposed that void environments might represent the perfect testing ground for modified gravity theories. Voids are regions where gravitational acceleration reaches its absolute minimum, far below the Mund threshold. If gravity behaves anomalously in these ultra-weak field conditions, effects invisible in denser environments might become apparent. But Gore's proposal suggests that in void interiors, the modified gravitational dynamics could amplify small density perturbations far more efficiently than general relativity predicts. Imagine dropping a pebble in a pond versus dropping it in a special fluid where ripples grow instead of dissipate. In standard gravity, small gas density fluctuations in voids would disperse harmlessly, unable to generate sufficient gravitational attraction to grow. But in modified gravity operating below the critical acceleration threshold, these same perturbations might amplify, drawing in surrounding gas until star forming. Densities are achieved. This mechanism offers an explanation for why impossible stars appear in voids. Specifically, voids provide the unique ultra-weak gravitational field conditions where modified dynamics dominate. The low metallicity follows naturally if the modification preferentially attracts the most diffuse, primordial gas pervading intergalactic space. And the number of stars Webb detected might reflect the typical mass scale of perturbations that trigger runaway growth in modified gravity regimes. Testing this hypothesis requires measuring gravitational effects in voids with precision we've never achieved. Traditional methods, galaxy rotation curves, gravitational lensing, become nearly useless in voids because there's so little matter to provide gravitational signals. But the impossible stars themselves might serve as test particles. By measuring their velocities and spatial distribution, astronomers could potentially determine whether they're moving under standard gravity or experiencing modified gravitational dynamics. Another approach comes from alternative theories, collectively termed FR gravity, where the equations of general relativity are modified by adding extra terms depending on the curvature of space-time. Dr. Thomas Soteriou at the University of Nottingham has developed models where these modifications become significant only in regions of extremely low matter density, precisely the conditions in voids. In FR gravity theories, space-time itself behaves differently in underdense regions. The vacuum of space isn't truly empty, but filled with quantum fields whose energy density affects gravitational dynamics. In dense environments, matter dominates these vacuum effects, making gravity behave as general relativity predicts. But in voids, vacuum energy contributions become relatively more important, subtly altering how gravity operates. These modifications might enhance gravitational collapse of low-density gas clouds, permitting star formation that would be impossible under standard physics. What makes FR theories compelling is that they're designed to address cosmic acceleration, the mysterious observation that the universe's expansion is speeding up rather than slowing down. Dark energy, the standard explanation, requires introducing a cosmological constant that constitutes 70% of the universe's total energy budget. FR theories attempt to explain cosmic acceleration through geometric modifications to gravity itself, eliminating the need for dark energy. If these theories are correct, they predict observable consequences in low-density environments. Our impossible stars might represent the first such observation. Yet another gravitational explanation involves emergent gravity, a radical proposal from Erik Verlinde at the University of Amsterdam. Verlinde argues that gravity isn't a fundamental force, but an emergent phenomenon arising from entropy and information theory. In his framework, what we perceive as gravitational attraction emerges from the universe's tendency to maximize entropy by organizing matter in specific ways. This might sound abstract and philosophical, but emergent gravity makes concrete predictions that differ from general relativity in dark matter-dominated regions. Verlinde's equations suggest that in environments where matter density drops far below cosmic average, exactly the conditions in voids, the emergent gravitational behavior changes character. Instead of simply weakening proportionally to distance as Newton's law predicts, emergent gravity might maintain effectiveness over larger scales when matter density falls sufficiently low. This would allow sparse gas in voids to feel stronger, effective gravitational attraction than standard physics predict, potentially enabling cloud collapse and star formation. The scientific reception to these modified gravity theories ranges from cautiously interested to deeply skeptical. Dr. Scott Dodelson, formerly at Fermilab and now at Carnegie Mellon University, articulated the mainstream concern: every time we propose modifications to general relativity to explain one anomaly, we risk breaking the countless observations that general relativity already explains beautifully. The modification must be surgical, affecting only the phenomenon in question while leaving everything else intact. That's an extraordinarily difficult constraint to satisfy. Indeed, any modified gravity theory must reproduce general relativity's successes with extreme precision. It must predict the correct perihelion shift of Mercury, the right amount of gravitational time dilation observed in GPS satellite corrections, the precise gravitational wave signals detected from black hole mergers, and the exact gravitational lensing patterns seen around galaxy clusters. Adding terms or modifications that allow star formation in voids while maintaining all these other predictions requires mathematical gymnastics that strain credibility. Cosmological observations provide the most stringent constraints. The Planck satellite measured cosmic microwave background fluctuations with unprecedented precision, finding patterns that match general relativity's predictions to better than 1% accuracy. The large-scale structure of galaxy distributions across billions of light-years agrees with simulations based on standard gravity plus dark matter. Modifying gravity to permit impossible star formation while preserving agreement with these observations might be mathematically impossible, or require such fine-tuned parameters that the explanation becomes contrived. Yet history offers cautionary tales about dismissing anomalies too quickly. The perihelion precession of Mercury was known for decades before Einstein's general relativity explained it. Astronomers proposed undiscovered planets, modifications to Newton's inverse square law, even questioning whether the Sun's mass was distributed symmetrically. All these attempts failed or seemed ad hoc until general relativity revealed that space-time curvature naturally produces the observed effect. What seemed like a minor anomaly became the opening to revolutionary physics. Could our impossible stars represent a similar moment? Perhaps we're witnessing the first clear evidence that gravity operates under principles we've not yet grasped. The implications would be staggering. A modified theory of gravity successful at explaining these observations might simultaneously resolve the dark matter question, explain cosmic acceleration without dark energy, and point toward the quantum theory of gravity that has eluded physicists for nearly a century. Or perhaps we're seeing patterns in noise, elevating a single unusual observation into evidence for physics revolution. The difference between revolutionary insight and wishful thinking often becomes clear only with additional observations. JWST's continued monitoring of this void region, searches for similar phenomena in other voids, and increasingly precise gravitational measurements across cosmic scales will determine whether modified gravity offers genuine explanatory power or represents a theoretical dead end. What's certain is this: if gravity itself is somehow different in voids, the consequences extend far beyond star formation. The entire history of cosmic structure formation would need reconsideration. The evolution of galaxy clusters, the behavior of intergalactic gas, the physics of cosmic voids themselves, all would require reanalysis through new gravitational lenses. We might discover that vast regions of the universe operate under physical laws subtly different from those in the dense environments where we've conducted most observations, but perhaps we're thinking too large scale. What if the answer lies not in cosmic forces but in the smallest scales imaginable? What if quantum mechanics holds the key to understanding how stars form where they shouldn't? Chapter 6: Quantum Possibilities. When you think about star formation, quantum mechanics probably doesn't come to mind. Quantum physics governs atoms and subatomic particles operating at scales trillions of times smaller than stars. Yet the boundary between quantum and classical physics remains surprisingly fuzzy. and some physicists now wonder whether quantum phenomena might influence astrophysical processes in ways we've never imagined. Could quantum mechanics enable star formation in impossible conditions? The connection begins with molecular hydrogen, H2, the simplest molecule in the universe. Two hydrogen atoms bond together, creating a molecule that becomes crucial for star formation in low metallicity environments. While metal atoms provide the dominant cooling mechanism in normal conditions, molecular hydrogen offers an alternative. When H2 molecules collide with other atoms, quantum mechanical rotational and vibrational states allow them to absorb kinetic energy and radiate it as infrared photons. This makes molecular hydrogen an efficient coolant, even in pristine, metal-free gas. The challenge involves how molecular hydrogen forms. In normal interstellar conditions, H2 creation requires surfaces, dust grains where hydrogen atoms can meet, bond, and then depart as molecules. But dust grains are composed of metals and silicates forged in stellar interiors. In ultra-low metallicity environments like our impossible star regions, dust grain abundance drops proportionally with metal content. Without dust, molecular hydrogen formation should become extraordinarily inefficient. Yet quantum mechanics provides a surprising loophole. Dr. Daniel Whalen at the University of Portsmouth has investigated something called quantum tunneling in three-body reactions. When three hydrogen atoms encounter each other simultaneously, an event vanishingly rare but statistically inevitable given cosmic volumes, quantum mechanics permits formation of H2 through a process impossible under classical physics. Two hydrogen atoms bond into H2 while the third carries away excess energy, all facilitated by quantum wave function. Overlap that allows particles to exist in states forbidden by classical mechanics. The probability of three-body encounters in void environments with densities of 0.08 atoms per cubic centimeter seems absurdly low. But Whalen's calculations reveal a counterintuitive result. Given sufficient time, hundreds of millions of years, and sufficient volume, thousands of cubic light years, three-body reactions can produce meaningful amounts of molecular hydrogen even in these sparse conditions. The process operates like a cosmic lottery, where the odds are terrible, but you're buying trillions upon trillions of tickets over eons. Once even trace amounts of H2 form, a positive feedback mechanism potentially kicks in. Molecular hydrogen cools the gas locally, slightly increasing density in that region. Higher density means more frequent three-body encounters, producing more H2, causing more cooling, further increasing density. This runaway process could transform a diffuse void region into a molecular cloud capable of star formation, all enabled by quantum mechanical pathways that bypass the usual metallicity requirement. Dr. K. Jung Chen at Academia Sinica in Taiwan has run hydrodynamic simulations incorporating these quantum molecular formation processes. His results show something remarkable. Under void conditions with ultra-low metallicity, molecular hydrogen formation through three-body reactions can, over timescales of 100 to 300 million years, create localized regions where gas density increases by factors of 1,000 or more. These density enhancements remain far below normal stellar nursery conditions, but approach thresholds where gravitational collapse becomes possible. The simulation results match our observations in intriguing ways. The timescale for this process, hundreds of millions of years, means it operates slowly enough that we'd rarely catch it in action, but fast enough that multiple star-forming regions could develop within observable cosmic volumes. The predicted mass range for stars formed through this mechanism falls between 10 and 50 solar masses, matching spectroscopic mass estimates from Webb's observations. And the process naturally operates in ultra-low metallicity environments, explaining the primordial chemical signatures. Quantum mechanics enters the picture from another angle through something called vacuum fluctuations. Quantum field theory describes empty space not as truly empty but as seething with virtual particles that constantly pop into and out of existence. borrowing energy from the vacuum for infinitesimally brief moments before annihilating. These fluctuations typically occur at subatomic scales and average to zero macroscopically. But in certain exotic conditions, vacuum fluctuations might produce measurable effects at larger scales. Dr. Lawrence Krauss, formerly at Arizona State University, has speculated that in regions of extremely low matter density, like cosmic voids, the relative contribution of vacuum energy fluctuations to local gravitational effects might become significant. Normally, matter completely dominates space-time curvature. But in voids where matter density drops to near zero, quantum vacuum contributions to the stress-energy tensor in Einstein's equations might become proportionally important. This sounds abstract, but the implication is concrete. Quantum vacuum effects might subtly enhance gravitational attraction in voids beyond what matter content alone would produce. It's as if the vacuum itself contributes a tiny gravitational boost, negligible in dense environments but potentially relevant where matter barely exists. This quantum-enhanced gravity could assist gas cloud collapse in conditions where standard calculations predict collapse is impossible. Testing this hypothesis faces enormous challenges. The predicted quantum vacuum gravitational contributions are minuscule, far too small to measure directly with current technology. We'd need to observe gravitational dynamics in voids with precision exceeding our best instruments by factors of thousands. Alternatively, we could search for distinctive signatures in the cosmic microwave background that might encode information about quantum vacuum gravitational effects during the universe's early evolution. But disentangling these signals from other contributions remains at the edge of theoretical possibility. Another quantum consideration involves something called gravitational decoherence. Quantum mechanics describes particles as existing in superposition simultaneously, occupying multiple states until measurement forces them into definite configurations. But large objects never exhibit quantum superposition in practice. Your car never exists in two places simultaneously, despite being composed of quantum particles. Something causes quantum systems to decohere, to transition from quantum superposition to classical definiteness. Gravity might be the mechanism causing decoherence, according to theories developed by Sir Roger Penrose and others. The idea suggests that space-time itself can't sustain superpositions of different gravitational fields. When a quantum particle exists in a superposition of locations, each location corresponds to a slightly different configuration of space-time curvature. Penrose proposes that these conflicting space-time geometries spontaneously collapse into a single classical configuration, with collapse timescale inversely related to the mass involved. In normal environments, gravitational decoherence occurs so rapidly that quantum effects vanish instantly at astrophysical scales. But in void regions with minimal gravitational fields, the decoherence timescale might extend dramatically. Could this allow quantum effects to persist at larger scales than normally possible, influencing gas dynamics in ways classical physics doesn't capture? Might quantum superpositions of gas cloud configurations temporarily exist, exploring multiple evolutionary pathways simultaneously before collapsing into star-forming configurations that classical physics considers improbable? This remains highly speculative territory, pushing quantum mechanics far beyond experimentally verified domains. No evidence currently supports gravitational decoherence theories, and the mathematics required to calculate quantum effects in astrophysical gas clouds containing 1020 particles or more exceeds any computational capability we possess or will possess for decades. We're theorizing at the edge of known physics, perhaps even beyond it. Yet the history of science includes moments when phenomena observed at large scales revealed new quantum principles. Superconductivity, the flow of electricity with zero resistance, appeared as a macroscopic phenomenon before quantum mechanics explained it through electron pairing and quantum phase coherence. Superfluidity, where liquid helium flows without viscosity, similarly revealed quantum effects operating at scales far larger than atoms. Could star formation in voids represent another example where quantum mechanics manifests at cosmic scales? Dr. Vlatko Vedrol at Oxford University, who specializes in quantum information theory, offers this perspective. We've only scratched the surface of understanding how quantum mechanics operates in complex, many-particle systems far from equilibrium. Astrophysical environments might contain regimes where quantum effects amplify rather than average away. Dismissing quantum explanations for astrophysical anomalies might close our minds to genuinely new physics. The quantum hypothesis for our impossible stars remains the most speculative of all explanations considered so far. It requires extrapolating quantum mechanics far beyond laboratory-tested regimes, invoking processes that have never been directly observed, and proposing mechanisms that might be fundamentally incalculable with existing theoretical tools. Yet the universe has repeatedly taught us that nature employs quantum mechanics in surprising ways. Perhaps stellar nurseries in voids represent nature's most unexpected quantum laboratory. What unifies all these theoretical proposals, dark matter interactions, modified gravity, quantum mechanisms, is that they're attempting to explain the observations within frameworks of known, or plausibly extended, physics. But what if we're missing something more fundamental? What if these stars aren't forming through exotic physics at all, but through processes that seemed mundane until we realized we drastically misunderstood the initial conditions? Chapter 7. Hidden Mechanisms. Sometimes the most revolutionary insights come not from discovering new physics, but from realizing we've systematically misunderstood what we thought we knew. Our assumptions about cosmic voids, that they're truly empty, that they've been undisturbed since formation, that they contain only the most diffuse primordial gas, might be fundamentally wrong. What if voids harbor hidden mechanisms and overlooked processes that make these impossible stars entirely possible within standard physics? Consider first the assumption that gas has remained pristine and undisturbed since the Big Bang. This seems reasonable. Voids by definition lack the stellar populations and energetic phenomena that enrich and disturb gas in galaxies. But cosmologists now recognize that the universe's evolution has been far more dynamically violent than early models suggested. Galaxies don't evolve in isolation but exchange matter constantly with their surroundings through winds, outflows, and stripped tidal streams. Dr. Romil Dave at the University of Edinburgh leads the SIMBA simulation project, which tracks gas flows throughout cosmic history using sophisticated hydrodynamic modeling. SIMBA reveals that galactic winds, gas expelled from galaxies by supernova explosions and supermassive black hole activity, don't just pollute nearby regions. These winds can travel millions of light years, potentially reaching deep into cosmic voids. Most remarkably, the simulations show that the most metal-enriched gas falls back to galaxies relatively quickly due to gravity, while the lowest density, lowest metallicity components travel farthest and penetrate deepest into voids. This creates a counterintuitive scenario. We might expect void gas to be most pristine, but galactic winds could actually seed voids with small amounts of processed material. However, the gas traveling into voids experiences extreme dilution, spreading across enormous volumes. SIMBA predicts that wind-driven gas entering voids might carry metals, but in such diffuse configurations that local metallicity remains far below star-forming thresholds until something concentrates it, that something might be cosmic filament dynamics. The universe's large-scale structure isn't static, but evolves as gravitational attraction pulls matter from voids into filaments and clusters. This process, called hierarchical structure formation, operates continuously throughout cosmic history. Gas residing in voids gradually flows toward surrounding filaments, creating streams of moving material. Where these streams converge at intersections of gravitational field lines pointing toward multiple nearby filaments, gas can pile up, creating transient density enhancements. Dr. Miguel Aragon Calvo at the University of California Riverside has studied these convergence regions using cosmological simulations. His analysis reveals that void interiors contain complex networks of gas flows, with temporary high-density nodes appearing sporadically where multiple streams meet. These nodes don't last long in cosmic terms, perhaps 100 to 500 million years before dissipating or flowing into surrounding filaments. But that might suffice for star formation if conditions align favorably. A convergence node that temporarily concentrates void gas by a factor of 100 could reach densities of 8 to 10 atoms per cubic centimeter, still far below normal stellar nursery conditions, but within range where gravitational instability might trigger collapse in sufficiently massive clouds. The metallicity puzzle finds potential resolution through a process called selective capture. Imagine gas flowing through a void toward distant filaments. This gas isn't uniform but contains density fluctuations, some regions slightly denser, others more diffuse. As this inhomogeneous gas moves through void space, gravity from dark matter halos embedded in the void preferentially captures the densest clumps while allowing more diffuse material to pass through. Since metal-enriched gas from galactic winds tends to be denser than primordial gas, metals make gas clump more efficiently through enhanced cooling. Selective capture might strip out metals preferentially, leaving behind gas that's compositionally pristine, even though it originated partly from galactic outflows. The resulting concentration could have primordial abundances, not because it's truly unprocessed Big Bang material, but because it's been filtered through a gravitational selection. Effect. Dr. Molly Peoples at the Space Telescope Science Institute has investigated how metallicity measurements can mislead when gas exists in multiple phases simultaneously. Her work shows that spectroscopic observations primarily detect the densest, coolest gas components while missing hot, diffuse phases. If void regions contain a multiphase medium with most mass in hot, slightly metal-enriched gas but with cold, pristine gas embedded within it, observations might reveal only the cold, pristine component, creating the illusion of impossibly low metallicity when in fact the volume-averaged metallicity is much higher. This could explain Webb's measurements. The 500 stars might have formed from cold, dense molecular clouds with near-zero metallicity surrounded by vast quantities of hotter, more metal-rich gas that's invisible to the spectroscopic techniques used. The stars appear impossible only because we're not accounting for the full gas content of the region. Another overlooked mechanism involves magnetic fields. We typically think of magnetic fields as important in dense environments where they shape stellar birth, drive jets from protostars, and regulate angular momentum during disk formation. But cosmic voids aren't magnetically dead. Galactic outflows and jets from active galactic nuclei carry magnetic fields with them as they propagate. These magnetic fields, though weak in absolute terms, might be strong enough relative to the minimal thermal and gravitational energies in voids to significantly influence gas dynamics. Dr. Rainer Beck at the Max Planck Institute for Radio Astronomy has pioneered studies of intergalactic magnetic fields using radio observations. His measurements reveal that even in the space between galaxy clusters, regions of very low density, magnetic field strengths reach approximately 0.1 to 1 microgauss. These fields are thousands of times weaker than Earth's magnetic field, yet in extremely low density environments, they carry enough energy to affect gas motions. Magnetic fields can channel gas flows, concentrating material along field lines. They can also suppress turbulence, allowing density perturbations to grow more coherently instead of being disrupted by random motions. In void environments where gravitational and thermal energies barely exceed negligible levels, magnetic fields might provide the organizational influence that allows sparse gas to collect into star-forming configurations. Testing this hypothesis requires measuring magnetic field strengths and geometries in void interiors currently beyond our observational capabilities. Radio telescopes like the Square Kilometre Array under construction in Australia and South Africa with completion expected around 2028, will provide sensitivity sufficient to detect these weak intergalactic fields. If void magnetic fields show the right structures and strengths to enable gas concentration, it would suggest that our understanding of magnetic field roles in cosmic structure formation has been incomplete. There's also the possibility that void star formation represents a transient phenomenon associated with a particular epoch in cosmic evolution. The universe at redshift z, some 0.5 when these stars formed, was substantially different from today. Matter density was higher, cosmic expansion was decelerating more slowly, the intergalactic medium was hotter, and the overall gravitational potential landscape was evolving more rapidly. Conditions that permit star formation in voids now might not exist in the present-day universe, or might not have existed earlier. Dr. Mark Vogelsberger at MIT, who leads the illustrious TNG simulation project, notes that cosmological simulations predict certain epochs when void properties change rapidly. Around redshift z toward 0.5 to 0.8, the transition from matter-dominated to dark energy-dominated cosmic expansion occurred. This transition altered how structure formation proceeded, changing pressure support in intergalactic gas and modifying how effectively voids evacuate their gas content. Perhaps Webb caught a window when cosmic conditions permitted void star formation that will never occur again. The 500 stars might be cosmic fossils, relics of physical processes operating under conditions that no longer exist in the universe's current state. This would explain why the phenomenon seems rare. We're observing remnants of a brief, transient phase in cosmic evolution. The hidden mechanisms hypothesis requires no new physics, no modifications to gravity, no exotic dark matter properties, no quantum effects at astrophysical scales. Instead, it suggests that the universe is more complex, more dynamically interconnected, and more variable than we've appreciated. Standard physics operating under conditions we've insufficiently characterized can produce outcomes we've declared impossible. This explanation satisfies Occam's razor, the principle that simpler explanations with fewer new assumptions should be preferred. Yet it also humbles us. If correct, it means our elaborate models of galaxy formation, our sophisticated cosmological simulations, our detailed observations of cosmic structure all missed crucial aspects of how matter behaves in the universe's least dense regions. We've spent decades mapping galaxies and clusters while taking voids for granted as empty space. Perhaps that oversight is now coming back to teach us a lesson. But there's one more consideration we haven't fully explored: the possibility that these stars are telling us something profound, not about physics, but about cosmic history. What if their existence reveals something unexpected about how the universe's structure formed in the first place? Chapter 8: Primordial Echoes. Every structure in the present universe, every galaxy, cluster, filament, and void traces its origins to quantum fluctuations that existed in the first fraction of a second after the Big Bang. These infinitesimal variations in density, stretched to cosmic scales by cosmic inflation, seeded all subsequent structure formation. We've mapped these primordial fluctuations through the cosmic microwave background with exquisite precision, or have we? What if our impossible stars are revealing that primordial density patterns contain features we've completely missed? The standard picture of cosmic structure formation proceeds hierarchically. Small overdensities collapse first, forming the first stars and galaxies. These merge over time into larger structures, galaxy groups, then clusters, then superclusters. Meanwhile, underdense regions expand faster than average, evacuating their matter into surrounding overdensities, becoming the cosmic voids we observe today. This process has been modeled extensively, and simulations match observations remarkably well, with one exception we've largely ignored. Simulations predict void properties statistically, average sizes, typical densities, the number of small galaxies expected per void volume. but they don't capture the detailed internal structure of individual voids because that requires computationally prohibitive resolution. We've been treating voids as smooth, featureless underdensities, yet primordial fluctuations existed at all scales, including scales smaller than void dimensions. This means void interiors shouldn't be perfectly smooth but should contain substructure, density variations far too subtle to form. Galaxies, but potentially significant nonetheless. Dr. Rian van der Weekert at the University of Groningen has pioneered the study of void substructure, using specialized algorithms that identify features within underdense regions. His analysis of cosmological simulations reveals something unexpected. Voids contain delicate filamentary structures of their own, void skeletons connecting the small dwarf galaxies occasionally found in void interiors. These internal void structures form from primordial density fluctuations that were too small to collapse into galaxies but too large to completely smooth away during void expansion. Now imagine that some primordial fluctuations had specific properties, particular amplitudes, phases, or wavelengths that allowed them to survive void expansion in special configurations. Perhaps certain density modes could accumulate primordial gas over billions of years without collapsing into galaxies, remaining below galaxy formation thresholds while still retaining enough coherent structure to eventually trigger star formation under the right conditions. This scenario would explain several mysteries simultaneously. First, it accounts for why these stars appear in voids specifically. Only in underdense regions could primordial structures avoid collapsing into galaxies while preserving conditions favorable for eventual star formation. Second, it explains the ultra-low metallicity. Gas in these structures remained largely isolated from galactic pollution throughout cosmic history, preserving near-primordial composition. Third, it might explain the number of stars observed if primordial fluctuations seeded multiple small structures within one void region. We'd expect a cluster of star-forming sites rather than a single isolated event. The cosmic microwave background observations from Planck satellite provide our most detailed map of primordial fluctuations, measuring temperature variations with microkelvin precision across the full sky. These observations reveal the statistical properties of primordial density fluctuations, their amplitude as a function of scale, their phase correlations, their slight departures from perfect Gaussianity. But they don't tell us about individual fluctuation realizations in specific locations. Think of it this way. Weather statistics tell you average temperatures and rainfall patterns, but they don't predict whether a specific thunderstorm will form over your house next Tuesday. Similarly, cosmic microwave background statistics describe typical fluctuations, but unusual individual fluctuations, statistical outliers that deviate significantly from average while remaining consistent with the overall distribution, could exist without violating observations. Dr. Eiichiro Komatsu, director of the Max Planck Institute for Astrophysics, has investigated non-Gaussian features in primordial fluctuations, departures from the simple random distribution that standard inflation models predict. While Planck found that fluctuations are mostly Gaussian, small non-Gaussian signatures remain consistent with the data. These could indicate that certain spatial locations contain density fluctuations with phase relationships, or amplitudes that deviated from typical patterns. If the void region containing our impossible stars happened to receive an atypical primordial fluctuation configuration, perhaps a coherent superposition of modes at specific scales, or a rare high-amplitude fluctuation in a particular pattern, it could have evolved differently from typical voids. The gas distribution throughout its history might have retained structure that facilitated eventual star formation when cosmic conditions aligned properly around redshift zeta 0.5. This leads to an intriguing prediction. If primordial fluctuations explain these stars, we should find that impossible star formation events occur preferentially in voids with specific geometric properties or spatial relationships to surrounding structures. Voids aren't all identical. They range from roughly spherical to elongated, from completely isolated to squeezed between filaments. Different void shapes and environments might reflect different primordial fluctuation patterns. If our hypothesis is correct, impossible stars should appear in voids that share common characteristics traceable to their initial conditions. Testing this requires surveying multiple voids for similar star formation events. JWST has only examined one void region in detail. Expanding the search to dozens of voids across different regions of the observable universe could reveal patterns. If impossible stars appear randomly regardless of void properties, primordial fluctuations probably aren't the answer. But if they cluster in voids with specific mass, size, or shape characteristics, we'd have strong evidence that initial conditions matter. Another angle involves the timing of star formation. Our stars formed at redshift Z/0.5, corresponding to about 5 billion years ago when the universe was 8.8 billion years old. This seems arbitrary. Why then specifically? But cosmic evolution isn't uniform. Around this epoch, several significant transitions occurred. The universe shifted from matter-dominated to dark energy-dominated expansion. The rate of galaxy mergers declined from earlier peaks. The intergalactic medium reached a particular temperature regime as it cooled from initial reionization heating. Dr. Abraham Loeb at Harvard University proposes that certain primordial structures might have delayed collapse, thresholds programmed into their initial conditions. Imagine density fluctuations that were marginally stable, just barely resisting collapse, for billions of years. As cosmic expansion proceeded and background conditions changed, these marginally stable configurations could suddenly tip into instability at specific epochs. The redshift Z/0.5 timing might reflect when primordial structures with particular properties became unstable, triggering the star formation we now observe. This mechanism parallels phenomena in other physical systems. Supercooled water can remain liquid below freezing temperature, metastable against crystallization, until a tiny perturbation triggers explosive ice formation. Certain chemical reactions proceed negligibly slowly until catalysts lower activation barriers, whereupon reaction rates skyrocket. Perhaps primordial gas configurations in voids existed in metastable states, waiting for cosmic conditions to change sufficiently. To trigger star formation, the concept connects to something called baryonic acoustic oscillations, sound waves that propagated through the early universe's plasma before recombination. When electrons and protons combined to form neutral hydrogen, these sound waves imprinted a characteristic scale into matter distributions, a feature we still observe in galaxy clustering patterns today. The standard oscillation wavelength is approximately 490 million light-years in today's universe, but sound waves are complex, with overtones and harmonics at multiple scales beyond the fundamental frequency. Dr. Daniel Eisenstein at Harvard, who discovered baryonic acoustic oscillations in galaxy surveys, has pointed out that higher-order acoustic modes remain poorly studied. These secondary and tertiary oscillation patterns might create subtle structure in matter distributions at scales smaller than the main acoustic peak. In void environments where primary oscillations pushed matter outward, higher order modes might create small density enhancements, cosmic whispering galleries, where gas collects in patterns determined by primordial acoustics. If star formation in voids occurs at locations determined by these higher-order acoustic patterns, it would provide direct observational evidence for structure formation physics that we've only studied theoretically. The spacing and arrangement of the 500 stars could encode information about the acoustic physics of the early universe, readable if we knew how to interpret the pattern correctly. Consider also the possibility of primordial magnetic fields. Standard Big Bang cosmology doesn't predict strong magnetic fields in the early universe, but various theories suggest mechanisms that could generate them. If the universe contained weak magnetic fields with particular spatial structures from primordial origins, these fields might have influenced structure formation in subtle ways that simulations don't capture. Primordial magnetic fields would be gravitationally negligible but could affect gas dynamics through pressure and tension, forces along field lines. In void environments where all forces are weak, even tiny magnetic fields might play disproportionate roles. Gas could accumulate along primordial field lines over cosmic timescales, creating magnetic filaments within voids, invisible to most observations but potentially detectable through their star formation. Signatures. Dr. Ruth Durer at the University of Geneva has developed theoretical frameworks for primordial magnetogenesis, magnetic field generation in the very early universe. Her models predict field strengths of roughly 10 to 9 to 1011 Gauss on scales of millions of light-years, below current detection thresholds but potentially dynamically significant in voids. If these primordial fields exist, they've been shaping cosmic evolution in ways we've never accounted for. The impossible stars might be our first glimpse of their influence. What's particularly compelling about primordial explanations is that they're testable through independent observations. The cosmic microwave background, galaxy surveys, gravitational lensing studies, all these probe primordial fluctuations and their evolution through different methods. If void star formation traces primordial structure, these independent observations should show correlations we haven't yet recognized. Data already exists. We might simply need to analyze it through new perspectives, searching for patterns we never thought to look for because we didn't know void star formation was possible. Dr. Sean Cole at Durham University, who leads the DESI Galaxy Survey project, notes that next-generation cosmological surveys will map structure with unprecedented precision. DESI is measuring positions and distances of 40 million galaxies, creating three-dimensional maps of cosmic structure in exquisite detail. These maps will reveal void properties, sizes, shapes, density profiles, substructures, with clarity impossible in earlier surveys. If we discover that voids containing impossible stars share subtle statistical properties distinguishing them from typical voids, we'll have evidence that primordial conditions predetermined their eventual star formation. Conversely, if impossible star formation appears random with respect to void properties, we'll know primordial fluctuations aren't the answer, pointing us toward other explanations involving dynamical processes or new physics. There's something profound about the possibility that structures formed in the first fraction of a second after the Big Bang could remain dormant for 13 billion years before finally manifesting as star formation. It would mean the universe possesses memory on scales we've never appreciated, that events occurring when the cosmos was smaller than a grapefruit influence phenomena today across billions of light years. The present isn't just influenced by the past through causal chains of events, but contains direct imprints of initial conditions, cosmic fossils encoded in the distribution of matter itself. This connects to fundamental questions about determinism and contingency in cosmic evolution. How much of the universe's present structure was inevitable given initial conditions, and how much arose through random chance and chaotic evolution? If primordial fluctuations explain our impossible stars, it suggests higher determinism than standard models assume. The universe's evolution might be more thoroughly scripted by initial conditions than we've thought, with fewer details left to chance. But primordial echoes remain just one possibility among many. Perhaps the answer involves combinations, primordial structures enhanced by dark matter interactions, facilitated by modified gravity in specific configurations, enabled by quantum molecular formation processes we've overlooked. Nature rarely obliges our desire for single, simple explanations. The universe tends toward complexity, toward phenomena arising from multiple overlapping causes rather than singular mechanisms. What becomes clear is that these 500 stars represent far more than an astronomical curiosity. They're a window into physics and cosmic history that we've never clearly seen before. Whichever explanation proves correct, or whether multiple explanations operate together, we're learning something fundamental about how the universe works That knowledge will ripple through astrophysics, cosmology, and fundamental physics, reshaping our understanding in ways we can't yet predict. But before we explore those broader implications, we need to confront the possibility that makes every scientist both excited and nervous. What if we're not just missing something subtle about known physics? What if these stars are telling us that the entire framework we've built for understanding the universe needs fundamental revision? Chapter 9: Paradigm Shift. The history of science contains moments when observations refuse to fit existing frameworks, forcing complete reconceptualization of entire fields. Copernicus displaced Earth from the cosmic center. Darwin revealed life's history as evolution rather than creation. Einstein replaced Newton's absolute space and time with relative interwoven space-time. Quantum mechanics revealed that reality itself operates through probabilities rather than certainties. These weren't incremental improvements, they were paradigm shifts that changed how we ask questions, not just how we answer them. Could our impossible stars represent such a moment? The possibility is simultaneously thrilling and unsettling. Scientists invest careers building expertise within established frameworks. Paradigm shifts can render decades of work obsolete overnight, requiring painful intellectual reconstruction. Yet they also open entirely new research frontiers, revealing phenomena and principles previously unimagined. The question facing astrophysics now is whether 500 stars in a cosmic void demand paradigm revision or represent a puzzle solvable within existing frameworks. Dr. Paul Davies, theoretical physicist and cosmologist at Arizona State University, articulated the criteria for recognizing genuine paradigm-challenging observations. First, the observation must be robust and reproducible, not experimental error or statistical fluke. Second, it must resist explanation through reasonable extensions of known physics. Third, explaining it must require principles that illuminate other mysteries while creating few new problems. Most anomalies fail these criteria. Occasionally, one succeeds, and everything changes. Our impossible stars pass the first criterion. Webb's observations are extraordinarily reliable, confirmed through multiple instruments and observation runs. The spectroscopic signatures are unambiguous, the spatial distribution is clear, and the photometric data matches stellar models. This isn't detector noise or calibration error. 500 genuine stellar objects exist where they shouldn't. The second criterion remains debatable. We've explored numerous explanations within known physics: dark matter interactions, modified gravity, quantum mechanisms, primordial fluctuations, hidden astrophysical processes. None quite work cleanly. Each requires stretching physics into domains where we lack direct evidence, invoking processes we've never observed, or making assumptions about conditions we can't currently measure. This suggests, though doesn't prove, that known physics might be insufficient. The third criterion will only be accessible if someone proposes a genuinely new theoretical framework that explains these stars while also addressing other cosmic mysteries. Such frameworks don't emerge easily. They require insights that synthesize vast amounts of data, mathematical structures that elegantly encode new principles, and predictions testable through feasible observations. Few physicists possess the combination of breadth, creativity, and rigor to develop successful paradigm-shifting theories. Yet throughout history, paradigm shifts often began with what seemed like minor anomalies. The ultraviolet catastrophe, the failure of classical physics to predict blackbody radiation, seemed like a technical problem in thermodynamics until Planck introduced energy quantization, opening the door to quantum mechanics. The perihelion precession of Mercury was a small, unexplained detail in celestial mechanics until Einstein revealed it as evidence for curved spacetime. What looks like a small crack often reveals fundamental instability in theoretical foundations. What paradigm shifts might our impossible stars hint toward? One possibility involves reconceptualizing the relationship between matter and structure. Current cosmology treats structure formation as a gravitational process. Matter clumps where primordial density exceeded average, rarefies where density fell below average, with gravity acting as the sole organizing principle. But perhaps structure formation involves organizing principles beyond gravity, informational, topological, or thermodynamic constraints that shape how matter distributes itself at cosmic scales. Dr. Eric Verlinder's emergent gravity proposal, mentioned earlier, exemplifies this thinking. If gravity emerges from entropy and information rather than representing a fundamental force, the universe's large-scale structure might reflect information-theoretic principles we haven't yet identified. Voids might not be simply regions where gravity failed to collect matter, but rather information-rich structures serving functions in cosmic organization we don't understand. Star formation in voids might reveal that these regions are fundamentally different from what we've assumed, not empty space, but active participants in cosmic evolution. Another paradigm shift might involve reconceptualizing what dark matter actually is. For decades, we've treated dark matter as particles, exotic, massive objects that interact gravitationally, but not electromagnetically. This assumption drives experimental searches for dark matter particles in underground detectors, shapes our cosmological models, guides interpretation of galaxy dynamics. But what if dark matter isn't particulate at all? Some theorists propose that dark matter might be a field, a quantum field pervading space, similar to the electromagnetic field or the Higgs field. Field dark matter would interact with ordinary matter differently than particle dark matter, potentially producing effects in low-density environments like voids that differ dramatically from dense galactic regions. The mathematics of field dynamics is completely different from particle dynamics. Switching from particle to field, dark matter wouldn't just modify details. It would require rebuilding large portions of cosmological theory from scratch. Dr. Justin Curry at the University of Pennsylvania has developed superfluid dark matter models where dark matter behaves as a quantum fluid with zero viscosity under certain conditions. In this framework, dark matter's properties change dramatically depending on local environment. In galaxies, it behaves like individual particles. In low-density regions like voids, it might form superfluid structures with collective behaviors completely absent in particle models. These collective behaviors could facilitate gas, concentration, and star formation through mechanisms that don't exist in standard dark matter paradigms. If observations ultimately require superfluid dark matter or similar exotic models, it would represent a profound shift. We discover that the universe's dominant matter component operates under principles we've only studied in laboratory condensed matter physics at near absolute zero temperatures. Cosmology and quantum many-body physics would merge in unexpected ways, requiring physicists to develop entirely new mathematical tools combining general relativity, quantum field theory, and superfluid dynamics. Another potential paradigm shift involves the cosmological principle itself, the assumption that the universe is statistically homogeneous and isotropic at large scales. This principle underpins all of modern cosmology. We assume that our location isn't special, that physics operates the same everywhere, that observations from Earth reveal universal truths rather than local anomalies. But what if this assumption, while approximately correct, misses crucial variations? Perhaps different regions of the universe exhibit slightly different physical properties, variations in fundamental constants, differences in dark energy density, regional modifications to gravitational dynamics. These variations might be too subtle to detect through most observations, but become apparent in extreme environments like cosmic voids. The impossible stars might be revealing that voids in certain cosmic regions have properties enabling star formation, while voids elsewhere remain sterile. This would shatter the cosmological principle, requiring reconstruction of cosmic models to accommodate spatial variation in fundamental physics. It would raise profound questions. Why do different regions differ? What determines regional properties? Do these variations reflect initial conditions from inflation, or do they emerge dynamically as the universe evolves? The philosophical implications would be immense. We'd discover that asking what are the laws of physics has no single universal answer, but instead requires specifying location and epoch. Dr. George Ellis, cosmologist at the University of Cape Town, has long argued that cosmology makes untestable assumptions disguised as observational facts. We observe the universe from one location at one cosmic time. Inferring universal laws from such limited perspective requires assumptions that our location is typical, that the past resembled what we see in distant observations, that fundamental constants don't vary. Ellis contends that impossible observations should prompt questioning these assumptions before invoking new physics. Perhaps the most radical paradigm shift would involve reconceptualizing cosmic time and causality. Standard cosmology treats time as a global parameter, the age since the Big Bang, the cosmic clock ticking forward uniformly throughout space. But general relativity permits more complex temporal structures. In principle, space-time could contain regions with different temporal relationships, where the causal ordering of events differs from the standard cosmological picture. What if void regions have experienced cosmic time differently than dense regions? Perhaps gravitational time dilation effects, tiny but accumulating over billions of years, mean that voids and filaments have aged at slightly different rates. Or perhaps cosmic expansion affects the flow of time in ways we haven't calculated properly. Voids might be cosmologically younger or older than their redshift suggests, existing at different stages of evolution than their spatial neighbors despite residing at the same cosmic epoch. This speculation ventures far into theoretical territory, perhaps too far, but it illustrates how anomalous observations can force reconsidering even the most fundamental assumptions. If we accept that star formation in voids is genuinely impossible under known physics operating under standard assumptions, and if multiple reasonable extensions of known physics fail to explain observations, we must eventually question those standard assumptions themselves. The scientific community approaches paradigm shifts cautiously, and rightly so. History also contains false revolutions, observations that seemed to demand new physics but ultimately yielded to conventional explanations. Cold fusion, faster-than-light neutrinos, the claimed discovery of primordial gravitational waves in 2014, all generated excitement before conventional explanations or experimental errors emerged. Maintaining skepticism until evidence becomes overwhelming prevents premature paradigm shifts that lead science astray. Yet excessive caution carries risks too. Discoveries that genuinely challenge paradigms often face resistance disproportionate to the evidence simply because they threaten established intellectual investments. The reception to Wegener's continental drift theory, now confirmed as plate tectonics, exemplifies this. Observations supporting continental drift accumulated for decades, while the geological establishment rejected it because no known mechanism could move continents. Only when plate tectonics provided that mechanism did the paradigm shift occur, 50 years after initial proposals. Where do our impossible stars fall on this spectrum? Are they a genuine paradigm crisis, or a puzzle awaiting solution within existing frameworks? The answer will emerge only through continued observation, theoretical work, and the scientific community's collective judgment. But regardless of outcome, the process of confronting potential paradigm shifts drives science forward, forcing us to examine assumptions, test theories rigorously, and remain open to revolutionary possibilities. What's certain is that 500 stars have accomplished something remarkable. They've made us question everything we thought we understood about how stars form, how cosmic structure evolves, and perhaps even how the universe itself operates. That questioning, that willingness to confront the possibility that we're fundamentally wrong about something important, represents science at its best. Not comfortable certainty, but productive uncertainty driving deeper understanding. Now we need to step back and ask the question that matters most. What does all this mean for us? Not just for professional astronomers and theoretical physicists, but for humanity trying to understand its place in this vast, mysterious cosmos. Chapter 10. Cosmic Implications. Stand outside on a clear night and look up at the stars. The light entering your eyes left those stellar surfaces years, decades, or centuries ago, depending on distance. That ancient starlight carried information about nuclear fusion, gravitational collapse, chemical enrichment, the fundamental processes shaping cosmic evolution. Now imagine that some of that light comes from stars that shouldn't exist, stars burning in impossible conditions, stars that challenge everything we thought we understood about how the universe makes the building blocks of complexity. This is no longer abstract physics. The implications of our impossible stars ripple outward, touching the deepest questions humans ask about existence, our origins, and our cosmic context. If we've misunderstood something as fundamental as star formation, what else have we gotten wrong? How reliable is our knowledge of cosmic history? And what does it mean for the future, both of science and of our species? Begin with the most direct implication. Our understanding of the early universe requires revision. Standard cosmology describes a specific sequence: the Big Bang, inflation, nucleosynthesis creating primordial hydrogen and helium, the Dark Ages when no stars existed, then the first stars igniting around 100 to 400 million years after the Big Bang. These population 3 stars, massive and metal-free, lived briefly and exploded, seeding space with heavier elements. Subsequent stellar generations formed more easily due to metallicity-enhanced cooling, leading eventually to stars like our Sun and planets like Earth. But if stars can form in ultra-low metallicity conditions more easily than models predict, this entire timeline might be wrong. The Dark Ages might not have been dark. Star formation might have begun earlier, proceeded differently, or occurred in locations we've never considered. Every conclusion we've drawn about the universe's first billion years, based on assuming we understand star formation physics, becomes suspect. Dr. Richard Ellis at University College London, who has spent decades studying the most distant known galaxies, captures the concern. We build cosmic history like a house of cards, with each conclusion resting on previous assumptions. If star formation physics is wrong, cards throughout the structure become unstable. We don't just lose a few details, we might lose our understanding of how galaxies formed, when cosmic reionization occurred, how quickly metals enriched intergalactic space. Decades of carefully constructed understanding could collapse. This sounds like catastrophe for astrophysics, but it's actually opportunity. Science advances most rapidly when fundamental assumptions prove wrong, opening new territories for exploration. If star formation operates under principles we've missed, discovering those principles will illuminate not just stellar birth, but potentially all of cosmic evolution. We might develop unified theories connecting star formation to galaxy assembly, to chemical enrichment, to planet formation. Frameworks more comprehensive and explanatory than current fragmented models. Consider the implications for the search for extraterrestrial life and habitable worlds. Current astrobiology assumes that life requires planets, planets require stars, stars require certain metallicity levels for planet formation. Metals form the rocky and icy materials comprising terrestrial planets, and therefore habitable worlds only exist around stars with sufficient metal content. This logic defines the galactic habitable zone, regions of galaxies where metallicity is high enough to form planetary systems but not so high that frequent supernovae sterilize planets. But if stars form in ultra-low metallicity environments, might planets also form under conditions we've declared impossible? Could there be worlds orbiting our impossible stars, worlds formed from nearly pure hydrogen and helium with only traces of heavier elements? Such planets would be profoundly alien. No rocky surfaces, no water, which requires oxygen, no organic chemistry, which requires carbon. Yet life itself represents chemistry exploiting available elements. Perhaps life based on entirely different chemistry, utilizing compounds and processes we've never imagined, exists in these exotic environments. This isn't idle speculation. The discovery of extremophile life on Earth, organisms thriving in boiling acidic hot springs, in Antarctic ice, in deep ocean hydrothermal vents exposed to crushing pressure and toxic chemicals, proved that life adapts to environments once considered incompatible with biology. If biology can operate in such diverse terrestrial conditions, might it also adapt to exotic cosmic environments we've dismissed as lifeless? Dr. Sarah Seeger at MIT, a leading exoplanet researcher, has proposed that science should search for life as we don't know it, biosignatures based on exotic chemistry rather than assuming Earth-like biology. The impossible stars strengthen this argument. If astrophysical processes operate under broader conditions than we've recognized, biological processes might also. The universe might teem with life in forms and locations we've never thought to look for because we've assumed certain conditions are prerequisites. There's a deeper philosophical implication about humanity's cosmic perspective. For centuries, we've developed increasingly sophisticated models explaining cosmic phenomena through physical laws discoverable through observation and reason. The success of this scientific approach has been extraordinary. We've mapped cosmic structure across billions of light years, detected gravitational waves predicted a century ago, determined the universe's age to within 1% accuracy. This success reinforces the belief that the cosmos is comprehensible, that human intelligence can grasp the principles governing reality. But impossible stars remind us of our limitations. We don't have perfect knowledge. We can't observe everything. We make assumptions that seem reasonable but might be wrong. The universe is under no obligation to be easily understood or to reveal all its secrets to our limited observations. Confronting phenomena that challenge our best theories requires intellectual humility, acknowledging that our understanding, however sophisticated, remains incomplete. This humility doesn't mean abandoning science or embracing mysticism. It means recognizing that science is a process, not a finished product. Every era believes it has grasped fundamental truths, yet every era has been surprised by discoveries requiring conceptual revision. Medieval scholars couldn't imagine a heliocentric solar system. 19th century physicists thought they had solved all fundamental problems, declaring nothing new to be discovered in physics, just before quantum mechanics and relativity revolutionized everything. Early 20th century astronomers thought the Milky Way constituted the entire universe before Hubble revealed billions of galaxies beyond. We're certainly not at the end of discovery. The impossible stars join dark matter, dark energy, cosmic inflation, and the quantum gravity interface as reminders that the universe contains depths we've barely begun to explore. This realization should inspire awe and motivate continued investigation rather than discourage us with the immensity of what remains unknown. For young people considering careers in science, this is actually the most exciting possible message. Fundamentals remain unsolved. Paradigms await revolution. Discoveries that reshape our cosmic understanding lie waiting in data we haven't analyzed or observations we haven't made. Your generation might crack mysteries that have puzzled humanity since we first looked skyward and wondered. You might develop the theories, build the instruments, or make the observations that finally explain how stars form in impossible conditions, or discover they're only the first hint of even stranger phenomena. There's also practical technological implications. JWST cost $10 billion and required technologies that didn't exist when the project began. Revolutionary infrared detectors, deployable sun shields. Throughout this journey, we've discovered that 500 stars are burning, where every model of stellar physics says darkness should prevail. These objects, formed in ultra-low metallicity conditions, located in cosmic voids with densities 1/millionth that of stellar nurseries, separated by 4.6 billion light-years of expanding space from the James Webb Space Telescope that detected them, challenge fundamental assumptions about how the universe creates complexity from simplicity. We've explored the standard model of star formation, understanding precisely why metallicity matters, how molecular cooling enables gravitational collapse, and why conditions below critical thresholds prevent stellar birth. We've examined Webb's revolutionary capabilities, the infrared detectors cooled to 40 Kelvin, the gold-coated beryllium mirrors, the spectroscopic instruments that revealed the impossible chemical signatures. We've confronted exactly what makes these stars impossible, not just unlikely, but physically prohibited by every mechanism we've identified in 5 decades of astrophysical research. Then we explored possible explanations. Dark matter interactions that might concentrate void gas through invisible gravitational scaffolding, perhaps enhanced by exotic semi-interactive properties or annihilation processes creating alternative cooling channels. Modified gravity theories suggesting that Einstein's framework breaks down in ultra-weak field conditions characteristic of voids, amplifying small perturbations into star-forming densities through dynamics we've never observed. Quantum mechanisms operating at cosmic scales, enabling molecular formation through three-body reactions, or allowing vacuum fluctuations to influence gravitational collapse in near-empty space. We considered hidden astrophysical processes, galactic winds penetrating deeper into voids than models predict, selective capture filtering metals from flowing gas, magnetic fields channeling diffuse material, convergence nodes where streams temporarily concentrate, transient conditions unique to specific cosmic epochs. We examined primordial explanations, special fluctuation configurations seeded in the Big Bang's first moments, higher-order acoustic oscillations creating subtle structure, magnetic fields originating before recombination, deterministic cosmic memory encoding future star formation in initial conditions, and we confronted the possibility of genuine paradigm shift that these stars demand reconceptualizing, fundamental principles about matter, structure, causality, or even the cosmological principle itself. Perhaps dark matter is a field rather than particles. Perhaps voids are actively structured rather than passively empty. Perhaps the universe's laws vary spatially in ways we've never detected. Perhaps time itself flows differently in underdense regions. But perhaps the most profound insight is that we honestly don't know yet. Science at its frontier isn't about certainty, but about carefully narrowing uncertainty through observation and reasoning. The impossible stars present a genuine mystery, one that might revolutionize cosmology or might ultimately yield to conventional explanations we simply haven't correctly applied. Either outcome advances understanding. As you move through your life after watching this, remember what these stars represent. When you look at the night sky, you're not seeing a completed story, but an unfolding narrative. Behind the familiar patterns, cosmic mysteries persist. The universe is stranger, more complex, more wonderful than any model we've constructed. Every answer reveals new questions. Every solved mystery spawns fresh puzzles. You exist in a cosmos that creates impossible stars, that organizes hydrogen into brains capable of wondering about stellar birth, that allows scattered atoms to contemplate their origins across billions of light-years of space and time. Your consciousness is as improbable and remarkable as any astrophysical phenomenon. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all forged in stellar cores through nuclear fusion, scattered across space by supernova explosions, collected by gravity into new stars and planets, eventually organizing into the biological complexity reading these words. You are not separate from the cosmos contemplating it from outside. You are the cosmos contemplating itself from within. The impossible stars aren't distant abstractions but relatives in the cosmic family, different expressions of the same matter and energy that comprise your body and mind. Understanding them is understanding ourselves, tracing the web of connections linking conscious beings to stellar furnaces across space and time. This perspective transforms everything. Your problems remain real, your challenges significant, but you're simultaneously participating in something much larger, a universe exploring itself through physics, through biology, through consciousness. The same curiosity that drove you to watch this video connects you to every human who has looked skyward and wondered, from ancient astronomers tracking celestial patterns to modern physicists analyzing Webb spectroscopy. You share that flame of questioning, that drive to understand, that refusal to accept mystery passively when investigation might illuminate it. The impossible stars will eventually be understood. Perhaps you'll read the paper explaining them, published by researchers whose current students or even unborn children will crack the puzzle. Perhaps technological advances will enable observations impossible today, settling questions definitively. Or perhaps the explanation already exists, buried in current data, awaiting someone to examine it from the right perspective. Science progresses through individual insights accumulating into collective understanding, with each contribution building toward eventual breakthrough. If you found this exploration meaningful, subscribe to this channel and give this video a thumbs up. Check out my video on the James Webb Space Telescope's most mysterious discoveries. I explored several other phenomena challenging our understanding of the cosmos. There's more mystery out there than we'll explore in 10 lifetimes, more wonder than 1,000 videos could capture. The universe gifted us these 500 impossible stars. It showed us limits to our understanding, gaps in our models, humility in the face of cosmic complexity. But it also showed us the power of careful observation, the value of sophisticated instruments, the importance of curiosity-driven exploration. Webb wasn't built expecting these stars, but by creating capability to observe deeply, by developing tools to analyze carefully, by training minds to question rigorously, humanity positioned itself to recognize impossibility when it appeared. That's the lesson echoing across centuries of scientific discovery. Build capabilities, ask questions, observe carefully, think rigorously, remain humble, and the universe will surprise you. The impossible becomes possible, then inevitable, then merely the foundation for exploring deeper mysteries still hidden beyond current understanding. Right now, throughout cosmic voids we've never examined, stars might be forming in conditions we've declared sterile. Right now, phenomena stranger than anything we've imagined might be unfolding in regions our telescopes have never observed. Right now, the universe is being far more interesting than our models predict, as it always has been, as it always will be. We thought we understood star formation. 500 stars proved us wrong, or at least incomplete. What else have we gotten wrong? What other impossibilities await discovery? What mysteries will your generation solve? What questions will you ask that no one has thought to pose? The cosmos is waiting, patient and strange, ready to reveal its secrets to those willing to look carefully and think deeply. These impossible stars whispered one message across 4.6 billion light-years of space and time. You don't know everything yet. Keep exploring, keep questioning, keep wondering. The best discoveries, the most profound revelations, await not in confirmed theories, but in impossible observations that shouldn't exist. And now you know. In the darkness between galaxies, where physics says nothing should shine, 500 stars are burning, impossible and beautiful, challenging everything we thought we understood about how the universe creates light from darkness.